now that we've had lunch, let's begin with part 4. And this is the final part where we're trying to put everything in increasingly more clinical relevance. And so I simply call it practical matters, where we'll review our formulas. We'll talk about prescribing glasses and some tricks related to that. Then we'll review instruments and how they work. And finally, a section I call optics in the office, where patients present with certain complaints, and you have to translate that into what does that mean about their glasses, or what do you look into their refraction that's a problem. So we officially have the 1 hour to cover these topics. I may run over a little bit, but should be able to come close to that. So here are those formulas again. Remember, the the most basic formulas of Prentice's rule, the Vergence formula, U plus D equals V, you kind of know that. Focal length is the reciprocal of the power. You see, by using them and applying them, they become more useful to you. Spherical equivalent is sort of trivial. And then the power calculations, yeah, that's a little bit more complicated. Definitely something you'd want to look at, say, the day before you were being tested, just to make sure you remember them. But I think I've repeated them enough that they at least make sense to you, including the SRK formula. It's a good idea to know that, just to, mainly because of the changes that you would make with changes in axial length or Ks. And then the magnification formulas, and we're going to revisit these as we look at some of the instruments that we work with. One, I just said image distance over object distance, but then the transverse is the square of the axial, and then a simple magnifier versus a telescope and spectral magnification. So that's it. That whole wall of formulas breaks down into these concepts that we've covered to some extent over the course of this day. So let's then talk first about, in this section, about prescribing glasses, retinoscopy tips, high index lenses, how to improve myopic lenses, dealing with night myopia and aphakic spectacles, what to do when a child won't wear glasses, prescribing astigmatic lenses, and working with a high-powered Jackson cross cylinder. So during retinoscopy, how do you modify the value obtained at neutralization to obtain the final refraction? And I've mentioned this earlier, but think about what we're doing when we're doing retinoscopy. We're taking the far point of the eye and we're putting it at the peephole of the retinoscope. And so, but if we gave that as the glasses prescription, then the patient would be in focus on the peephole of the retinoscope, and we don't want that. We want them in focus at infinity. And so we need to move the far point to infinity, and we do that by subtracting the reciprocal of the distance to the patient from the number that we get. For most patients, it's 2/3 of a meter. Reciprocal of that is 3/2, or 1.5 diopters. What if a patient has a difficult to interpret retinoscopic reflex? Here's a LASIK flap gone bad, and that's going to be a very irregular retinoscopic reflex. How do you work with that? Well, one is, don't forget, you can move closer. So sometimes, even in a child, I'll move till I'm just 10 centimeters away, and at least that gives me the cylinder and one compared to the other. And you know, it's a little tricky because it's 1 centimeter one way or another is a whole diopter at that distance, but you know, it's basically you would subtract 10 from that number. So move closer. Concentrate on the center of the reflex, as I mentioned with spherical aberration. You get better and better as you do more retinoscopy on just looking at the central part of the retinoscopic reflex. If the astigmatism is irregular, then consider a contact lens over refraction, because that'll take away a lot of that irregularity and give you the best visual acuity you can get. You can always try the autorefractor. It might not work if it's not possible to retinoscope. You could get up with a bad number. You could just go ahead and throw up random numbers and do a subjective refinement of the refraction. Or another option is to use the stenopeic slit. And we don't really have time to go into how to do a stenopeic slit refraction, but it involves finding the major axis of astigmatism, using sphere to neutralize, and then going 90 degrees away and using sphere to neutralize that, ending up with a power across that you then convert to glasses prescription. Or you could just prescribe the patient pinhole glasses, which will neutralize any refractive error, and it's a form of natural vision therapy. Now, what are high index lenses? Well, high index lenses are plastic, generally plastic lenses with a refractive index of 1.66 and up. They're thinner lenses and lighter weight. And why is that? Well, remember the equation, D equals n prime minus n over r. Well, r is the curvature, but if n prime minus n is a bigger number, then you don't need as much curvature to get the same diopters of power. So if you need less curvature, then the lenses are going to be less thick at their edges. So generally, high-index lenses are helped. They are going to be more expensive than ordinary plastic. Some have less light transmission. Some have more chromatic aberrations. So they're not perfect, but they are definitely have advantages. There are even glass lenses that you can get in Europe that have a 1.8, and patients swear by them. You can't get them in the US because they don't meet safety standards here. So if your patients always go to Germany to get their glasses made, then that's probably why. Patient comes into your office, says, gee, doc, can't you do something about these thick glasses? They look terrible. And you say, yeah, they do look terrible. So what can you offer to this patient? Well, how do you improve the appearance of high minus lenses? Well, again, we just mentioned one method. Well, before we get to that, make sure the patient's not over minus. Now, it's not like he's wearing minus 20 glasses. You're not going to get him to minus 2, but if you can knock another diopter or so off, that wouldn't hurt. So cycloplegic refraction. Next would be to use smaller frames because the curvature, the more curved they are, the thicker they get as you get out to the periphery. So if you could have very small frames, they're just not going to look as thick at their edges. So that's a simple way. And the lenses can be beveled and polished at their edges in certain ways. And then the key, the money answer is, use that high refractive index material because then you use less, you need less curvature to get the same refractive power. And then plastic versus glass, well, that depends because as I just mentioned, some kinds of glass are actually less heavy, but at least in the US, you do better with plastic. A flatter base curve for the front of the lens, that is, I mentioned earlier that lenses have this sort of meniscus shape so that the front tends to have plus power on it, even for myopic patients. But if you flatten that out, then you have to scoop less out of the back to get the same myopic correction. And then frames that hide the thick edges can help as well. And in real life, you would also offer the patient contact lenses or possibly refractive surgery depending on their situation. So that's the different ways to improve the appearance of high minus lenses. 27-year-old patient returns to you after careful refraction. He's complaining of continued trouble with distance vision, especially at night. I seem to be night blind, he says. What are some causes? Well, after you've ruled out retinitis pigmentosa and patient unable to find their way to the seat in a dark theater, but just having trouble seeing road signs at night, then you want to look for the causes of night myopia. And that would include pupil dilation. So in the dark, the pupils get bigger, so there's more spherical aberration, which increases the myopia because of the positive spherical aberration. Plus, just a bigger pupil is going to reveal irregular astigmatism as well, which further degrades the image. Second is the length of the refraction lane. When we refract a patient, it's in a 20-foot long lane indoors, but when they're in a car, they're looking at signs that are 100 feet away or more. And so we want to, so the patient's not truly corrected for infinity if you refine the refraction in the office. To correct for infinity, you subtract that distance from the end of the exam lane, which is 1/6 of a meter, from the final prescription to put it truly off at infinity. Well, you're not going to subtract 1/6 of a diopter, but you could put an additional minus 0.25 into their glasses. Then this is a little fancier answer. Lower light levels cause a Purkinje shift. That is, photoreceptors are more sensitive to blue in low light. You can tell that from watching television because they always show that it's nighttime because everything is blue, has this sort of bluish hue when they, but photoreceptors are more sensitive to blue in low light. And remember, from chromatic aberration, that's going to move the focal point anteriorly and make the patient more myopic. And then finally, in the dark, there's not as many accommodative targets. Patients may focus on a headlight and over-accommodate and fog himself to further cause night myopia. So all of these things can be mediated by giving a little bit more minus in the glasses. He's 27, so he can take being over minus probably, but as patients get closer to being presbyopic, they may have to have separate driving glass, sort of night driving glasses that over minus them slightly if they really are complaining bitterly about this condition. Problems with aphakic spectacles. Well, you know, we don't deal with aphakic spectacles much, but we do have a lot of little hyperopes running around in the pediatric ophthalmology. There's a ring scotoma secondary to the prismatic effects of the edge of the lens. There's pincushion distortion, sort of the opposite of what I showed you when I turned the indirect lens upside down. The magnification that we discussed earlier, and the weight and cost of these spectacles. Sort of intuitive stuff, but worth at least mentioning explicitly while you're thinking about it. What if a child won't wear his glasses? What can you suggest? Well, a lot of times it's more to do with the frames than anything, because some opticians just don't have the selection or don't know how to fit kids. I mean, gee, I wonder why he doesn't like wearing these glasses. Perhaps because they cover one eye and they're made for a 32-year-old. They're actually the same glasses as that other guy was wearing. So the frame needs to fit properly. Opticians may not want to deal with kids and not take the time, and they have to be adjusted frequently because they get bent all the time, and a kid whose glasses don't fit, he's not going to say, it's bothering me right here. He's going to put the glasses in the toilet. Consider a short course of cycloplegia to remind the patients why that the glasses actually do help, hyperopic patients, the glasses do help them see better. Who would have more trouble adjusting to contact lenses, a pre-presbyopic myope or hyperope? This sounds like almost a trick question, because you would think that as long as the refraction is corrected, it should be the same at near. But remember, at near, it's diverging light coming into the eye, not parallel rays of light. And so glasses, spectacle lenses, are going to see a different divergence than contact lenses. Furthermore, the power of the spectacle lens is going to be different than the power of the contact lens because of vertex difference changes. And so we could work through the math, but I'm just going to tell you to remember that it's the myope. Myopic patients will have more trouble adjusting to new contact lenses because there is a greater accommodative demand accommodating through contact lenses than through glasses in the case of myopia. The opposite is true as in hyperopia. So the divergence from the near target is greater after entering the eye through a contact lens. There's also a prismatic effect that can help you remember if you can't completely memorize it, want to figure it out. Minus lenses, remember, act like base in prism when the eye converges. Well, that's going to help the myopic patient converge when reading through minus lenses. You take those away, now they're going to have to converge all the way on their own. What are the disadvantages of progressive addition lenses? Why don't all patients wear them? Well, to get this channel of variable magnification through the no-line bifocals, you end up with this peripheral irregular astigmatism. These channels, the designs can vary. They can make them wider or narrower, speedier, increase in power, or less speedy, but the end result is this kind of distortion. So an architect, a draftsman, an art historian, these are the kinds of patients of mine who've had trouble with these progressive lenses and have had to switch to a segmented bifocal. The segment height is also difficult to adjust, and so if it's off by a little bit, either they got to go too far down to get the power, or they're getting some of their near power when they're looking straight ahead. How do you deal with a patient who's not accepting spectacle correction of astigmatism? Well, why would a patient have trouble with astigmatic correction in glasses? Well, this is what happens, is you get this kind of distortion of the image from the astigmatic correction, and the greater the vertex distance, the more. So, and not only is it the distortion, but there's another more subtle problem that develops, and it has to do with your binocular visual system. That is, here's what a door might look like to a patient who has astigmatic correction in both eyes that they're not used to. So each door looks a little distorted, it's true. But what you also get is you get this little bit of disparity, retinal disparity between the two eyes. Well, what's your binocular vision system primed to do? It takes retinal disparities and it builds them up into a three-dimensional perception of the world. And you can try to kind of cross your eyes and look at this image and get the two doors to sort of fuse into one. And if you do that, then you'll see, I can sometimes do it, it's pretty exaggerated, but what you'll see is the door isn't just distorted, but it looks like it's coming towards you. And that's just what the patients, they say. They say, oh my God, I put these glasses on and the floor's coming up at me and the walls are caving in. And it's not just because squares are oblique, it's because they have binocular distortion that's very disturbing to them. So how do you fix it? Well, you want to get away from oblique astigmatism if you can, or to reduce the astigmatic correction. You can actually try to fix it by reassuring the patient and just asking them to stick with it, and it'll get better. And even in older patients, I've found that that's possible to do depending on the patient. The longer it takes for the patient's older. If you can reduce the vertex distance, ultimately that would mean contact lenses. They're not going to cause much distortion. But if they happen to have some odd frames that kind of stick out, more than usual or something, then that would be one thing. It's more of just an answer to give you, but than anything I've actually prescribed. Cylinder lenses are ground both on the inside as minus cylinder or on the front as plus cylinder. They almost never ground on the front as plus cylinder anymore, but every now and then that's done, and that can exaggerate the astigmatic distortion. So minus cylinder lenses have less distortion. If those things don't work, then you do have to compromise visual acuity either by rotating the cylinder to 90 or 180 so you don't have that oblique distortion, or simply reducing the power of the cylinder, eventually trying to work the patient up to their full correction. There's always contact lenses or even refractive surgery to consider as well, of course. And my brother's friend Jack was noticing the body piercing trends and gave me this suggestion of a way to reduce the vertex distance by binocular piercing. Just take the little pierce here and then hang it. Then you can reduce the distance from the eye to the lens in this method. I haven't seen this catch on just yet. Why are there different Jackson cross cylinders? That is, you may not have, there's only one on the phoropter, but if you look around in the drawers of the office, you'll see something that looks like this. It's not a spoon. It's a Jackson cross cylinder, and there are different powers up to plus and minus 1. And the reason is that the poorer the visual acuity, the more difficult it would be for the patient to say which is better, 1 or 2. And of course, and the end point of Jackson cross cylinder is when they say they're the same. And so if the patient has 2200 vision and you're flipping a plus and minus a quarter, they're not going to see a difference. So you'll say, which is better, 1 or 2? They're going to say, it's the same. You'll say, good, we're done. But you actually haven't helped their refraction. So lower visual acuity, if you really want to refine the cylinder, you need a higher power Jackson cross cylinder so that they can see that difference. I just used that the other day with a 8-year-old child, and it actually worked. The fellow was stunned. So those are just some practical, aspects of prescribing glasses in patients, adults and children. And what I want to go to next is to look at the optical principles of some of the ophthalmic instruments that we use on a daily basis, and to try to better understand exactly how it is that they work. So we're going to talk about everything from the lowly trial lenses and lens clock to Lensmeter's retinoscope, how keratometry and slit lamps work, Applanation tonometry, then Fundus lenses and lasers. Trial lenses. So we use trial lenses in the office, and you would think, again, 1 + 1 should always equal 2, but if you don't actually separate the spacing just right, it doesn't add up. But the trial lenses are designed to have that kind of additivity, and the trial frames, are actually designed to take advantage of that, to put the lenses in the proper position. Those trial frames, they're awfully expensive for something that breaks all the time, but I guess that's why. So when you're using the trial frames, you want the numbers to face forward, and you want the high power sphere to go in the rear cell, because that's where the vertex distance matters most. And then any cylinder is going to go in the middle cell, and if you need another quarter low power lens, that would go in the very front cell, or prism, or whatever. So you would think that you're being a good industrious and studious, and you have this kind of new prescription for a patient, so you're afraid they might not accept it. Maybe it's got some cylinder in there that might be too much. So you go and you put it in the trial lens frames and you have the patient walk around the office and they say it's okay, they still might come back and say that the glasses are no good. And the reason is that they don't fully simulate dispensed spectacles because of differences in the aperture, in the base curve, and so just be prepared for that eventuality. A lens clock is something that you use in the office to determine the curvature of a lens. The dial here reads in diopters of surface power, assuming a certain refractive index of the lens behind it. So the conversion to surface power uses that refractive index of crown glass for this style. So there's a little pin here that moves back and forth, and depending on the position, the dial moves to a different place, and then you can judge the power of the lens on the back and on the front. There's a different kind that's made for plastic lenses, so you would want to be careful because usually the situation is the patient likes their old glasses, they don't like the new glasses, and you're trying to see a difference, and you can use the lens clock to tell. And if you use the wrong lens clock, you'll end up scratching their only glasses they ever liked in the world. So you want to be careful about that. So the way you use it is you can measure, you can see if there's a difference in base curve between eyes, and you can also see is there cylinder on the front surface or on the back surface of the lens. Probably the most typical scenario would be a patient comes into your office and they're on their way out the door after you've already finished the examination, and they say, "Oh, by the way, doc, can I have a new glasses prescription?" Now, of course, you didn't even do the refraction. You've already dilated the pupils, and you just want to go home. And so you just write out, you copy the exact prescription that they were already wearing. You say, here's your new prescription. So they go back, they get the new prescription made, and they come back 2 weeks later and they say, "Doc, these new glasses you prescribed, they're terrible. They're nothing like my old glasses. Those were great." So what are you going to do? You measure them in the Lensmeter. They're exactly the same power. And so perhaps there's a difference in base curve, the curvature, overall curvature of the lens. So you get out the lens clock and you compare the two, and you see if the base curve is different. And if so, then you have your diagnosis. Now, meanwhile, of course, your partners examine 3 patients and sign 2 of them up for surgery. So if you're smart, you never touch one of these things. But that is probably the most typical application. Lens clock. Next is Lensmeter. So the Lensmeter is used to measure the power of a spectacle lens. And when I say Lensmeter, I want you to think optometer principle. So what is the optometer principle? Well, think about trying to build a Lensmeter when how do you figure out the power of an unknown lens? Well, you might take a target and you might position the unknown lens next to your own eye. This is you, the examiner. And if you move that target to and fro, when you get it to just the right spot, you'll have parallel rays of light coming out. So you'll know that's then you take the reciprocal of the distance, and that's the power of the lens. The problem with that is that as you get closer to higher powers, tiny movements give big shifts in the dioptric power. Plus, how do you measure a minus lens that way? Then you have to slip some other lens in place or something. So it just doesn't work well. So the optometer principle says if you, there we go, so that's the power of that lens, but it doesn't work well. So the optometer principle says you add a second lens called a standard lens. You put the unknown lens at one focal point of that lens, and the target goes at another. When there's no lens in there and the target's at the focal point of the lens, then you, the examiner, are going to see parallel rays of light. However, if we now slip an unknown lens into the other focal point of the lens, of the standard lens, that's going to cause the rays of light to be unparalleled and out of focus. So now we've got to turn a knob, move the target, say closer in this case. So now parallel rays of light are coming out. So the advantage of the optometer principle with this standard lens is you get a linear scale and you can go from plus to minus power in measuring an unknown lens. So that's basically what a Lensmeter is with a little bit added on. So here's the Lensmeter, here's the target, it's illuminated. You turn a knob, it moves it back and forth. There's the standard lens inside of the Lensmeter, and here's where the unknown lens goes. Then you throw an astronomical telescope on there just to eliminate the examiner's refractive error and to further enhance the detection of parallel rays of light coming out. So that's all there is to it. So when you're using a Lensmeter, the way that I do it is at the beginning of the day, I'll actually have nothing in the Lensmeter, set the knob at 0, and then adjust the eyepiece, start by fog myself by turning the eyepiece out, then just dial it just in until the reticles and the target come into perfect focus. Then you know it's zeroed for your eye and should be accurate for the rest of the day. This is what you see when you look in a Lensmeter. The cross target with a sphere line and the 3 lines for the cylinder for the 2 meridians of astigmatism and power. When you're measuring the lenses, you want to measure the back vertex power. That is, the temples should be away from the examiner, except for the bifocal power add, which you measure when you're measuring the front vertex power, which is with the temple toward the examiner. That's especially important with high plus lenses. You can otherwise get fairly big differences if you try to just measure back vertex power for both. Now, normally, when you put a lens in and you look inside, you'll see this target exactly centered in these rings, and that's fine. But when you have Prism in there, then you'll see a displacement like so. So you hear this crossbar is displaced upward, and up here, right there, is a number 2. So that's 2 prism diopters, that's 1. So this is 1.5 prism diopters, and what you see is what it is. So it's 1.5 prism diopters of base up prism in that lens. Now, when you move the lens, if the lenses are, say, high plus or high minus, when you move them around, then that's going to change. But if it's a lower power, then it's more clear that that's the answer. I'll show you in a second what to do when they're higher power lenses to control for that problem. But if you forget this rule and you just want to use a neutralizing prism, you could put Prism in the path of light to recenter that cross in the middle. So that's what's being done here. In this case, it must have been horizontal prism because there's base out prism that's neutralizing. And so that means the glasses must have base in prism. There's also, in some Lensmeters, this little area to put in a tri-lens prism, or the ones that they sell now have a knob that you can dial in more or less prism. So this is what you do, this high-tech method to see where the line of sight passes through the spectacle lens. You just put a dot right in the center of each pupil, and that's where you measure the prism power. So then you don't have to worry about where the optical center is. In fact, sometimes the optical center can become displaced either by accident or on purpose and generate prism power. I even had a patient who had glasses not unlike these, who came back to the office, and she used to have an esotropia of 10 or something, and she came back, and now the esotropia was gone. But when I forget, I had to measure the glasses for something, and I discovered that the optical centers were like here, temporally, and here. And I got more history, and it turned out the glasses had fallen, had broken, or she dropped the glasses, both lenses had popped out, so they just popped the lenses back in. But they switched them, because they're symmetric lenses, and so they ended up decentering the optical centers. So then I needed to write a new prescription anyway because the glasses were broken, and I put on there, I put on the prescription, decenter optical centers, 1.5 centimeters temporally each eye. Got a call back from the optician, well, we can't do that. And I said, well, what do you mean? You just did it on these glasses when you fixed them last week. So it's sort of like that guy who goes to the airport and he says, I want this bag to go to Albuquerque and this bag to go to Chicago and this one to Denver. And they say, we can't do that. And they said, well, you did it last week. Decentering optical lenses. Again, if nobody laughs, I still get paid. You can also measure lens prism power with Lensmeters. They'll just spit it out for you using various approaches. The Retinoscope, what I want to mention about that is that it has a linear filament that produces, for the most part, divergent light. Now, the sleeve position can create convergent light, but it's only in special circumstances that you want convergent light going into the eye for retinoscopy. It should be divergent light most of the time. So you can, if it's a new retinoscope that you're not familiar with, you can do what I call the sleeve test, which is aim it at your sleeve and then push the sleeve all the way up, see if you can focus the light, push the sleeve all the way down, see if you can focus the light, and if you can focus the light, then that's not what you want. You want it to where you can't get it into focus, and that's where you position the sleeve for retinoscopy. How do we get these with and against movements when we do retinoscopy? Again, let's go back to the definition of what happens at neutralization of retinoscopy. At neutralization, as soon as the light goes into the eye, all the light coming back from the eye is focused at the peephole of the retinoscope, so it all fits through the peephole, so the pupil appears to fill with light the moment any light comes in, neutralization. If, however, the eye is not in perfect focus, say the far point is back here, well now when the light enters the eye, some of it coming back fits through the peephole, but the rest doesn't. It hits the edge of the peephole. So only part of the pupil appears to have light coming back. And the top stays on the top and the bottom stays on the bottom. That's with movement. However, if the far point is in front of the examiner, then what happens is the same problem. Not all the light gets through, but now the top has crossed over at the far point, the bottom's crossed over, and so because of that crossover, you get what appears to be against movement. Next comes the concept of optical doubling, and this is going to tie back into the vernier acuity discussion that we had some months ago. So remember the definition of a prism diopter is that 100 centimeters, a 10 prism diopter prism will displace an image by will displace the light by 10 centimeters. So in this case, we have a pair of sunglasses. And we have a 10 prism diopter prism. And if we can work it to where we can see both the object and the image at the same time, then we'll see that they're separated by 10 centimeters. What if we want to measure how high these sunglasses are? Well, let's turn back the prism, say it's variable. We'll dial it down to, say, 5. So now the separation is 5 centimeters. So that means that we can measure the height of these glasses must be 5 centimeters when the bottom of the image tops the touch of the object. Well, you say that's kind of a cumbersome way to measure something, but the beauty of this is that if those glasses, that the image and the object, if there's any movement or high magnification, they're going to move at the same time. So say those sunglasses are on a child, and say the child's jumping up and down on a trampoline, it's okay because the image and the object are moving at the same time, and so you can still make that adjustment to where they touch each other. Well, we don't go measuring necessarily glasses on children who are jumping on trampolines, but we do have to measure things on the surface of the eye under high magnification. And so this ability to use optical doubling or image doubling is invaluable. And it also takes advantage, you'll see later, of your vernier acuity because you're trying to make a line join to a line. So let's talk about that a little bit more, and in particular with regard to corneal curvature assessment. When we want to know how curved the cornea is, we generally do keratometry, optical or automated. Today we'll focus on just optical keratometry. There are other ways to do it too, we'll briefly mention. But for optical keratometry, you want to know how curved is the cornea. Well, how curved is the cornea means how strong. One way to determine that is to ask how strong a mirror is the cornea. And one way to determine that is to say how big is the image created by the cornea. So to determine that image, we project a mire onto the cornea and measure its size. An optical keratometer then looks at the average curvature over the central 3 millimeters of the cornea, measuring the size of a reflected mire. The size tells you the reflecting power. The reflecting power then allows you to determine the radius of curvature. The radius of curvature then allows you to infer the refracting power. And it uses optical doubling to do that. Let me show you an example. This is the Javel-Schiatz type of ophthalmometer, keratometer. It projects these two mires, the box thing and the Space Invaders thing, onto the surface of the cornea. So then you end up with an image that looks like this. Now, first of all, if you're not in line with a principal meridian of astigmatism, these are going to be just skewed like this. So you rotate, so you can rotate this thing to get them in line with the principal meridian. So we do that, rotate the mires. Now we're in line with the principal meridian. Now in this case, they're at the correct separation. But what if you have a very curved cornea? If the cornea is very steep, it's going to be a stronger minus power, so the image is going to be smaller. So now we're going to turn another knob, and it's going to change the separation of those mires to bring the images closer together. What if you have a weak or flat cornea? Then the images are going to be big, so you turn the knob, change the separation, increase it this time, and get your exact result. So that's basically what you're doing when you're doing keratometry. And you do a vertical meridian measurement, and you do a horizontal meridian measurement. So with this style, you have to do 2 measurements, but you get your 2 powers, and then you read it off here. You get the radius of curvature from the size of the mire, and then that corresponds with a certain power in diopters, assuming that the refractive index of the cornea is 1.3375, which it generally is. So that's that question about, someone asked me at the break about converting from radius of curvature to power, diopters of power. So now if the person was an alien from outer space and you did keratometry, then the radius would still be correct, but you might not know if the refracting power is truly this because you don't know what their cornea is made of. It might have a different refractive index. So you see, not only are you saving people's lives by diagnosing a ciliary body tumor through a refractive index change, or saving the world by keeping nuclear power plant operators in the proper bifocals, but you're also even learning how to do intergalactic keratometry. The Bausch Lomb keratometer is similar in its concept, but this projects the mires and allows simultaneous measurement of vertical and horizontal. And it uses image doubling to help you find your endpoint. That is, here if the keratometer is out of focus, you adjust it, you get a doubled image and adjust it to and fro until you have a single image. So it's using your vernier acuity to help determine that point of focus. And then if you're off axis, again, you turn it until you're on the axis of the principal meridians. Now you adjust the horizontal till it just lines up like so, and then you adjust the vertical till it just lines up, again using vernier acuity to make that precise measurement of the endpoint. A powerful cornea is going to have smaller mires, so you have to move them closer together. A weaker cornea, bigger mires. Here's an example of a flat vertical meridian, so you're going to have to increase the separation more vertically than horizontally. Then you look at the number on the keratometer to get your answer. Again, there are automated keratometers that automatically measure the size and position of these reflected mires. There is also, of course, corneal topography that one form that looks at these projected mires and then uses a computer to determine the separation and to convert that into a map of the corneal curvature over the whole surface of the cornea, rather than just an average keratometry that optical keratometers will calculate. So that's keratometers. Next is a slit lamp. And the key, there's Goldstrand again. When he wasn't busy winning a Nobel Prize, he was off inventing the slit lamp. And that is the key advance. When I say slit lamp, I want you to think common pivot point. So there's an illuminated slit that's projected into the eye, and a viewing system of a binocular stereo microscope with individually focused eyepieces. But the key is that they're imaged over a common pivot point so that as you move the slit lamp to and fro, the slit stays in focus and the place where you're looking at the slit also stays in focus. This gives you an optical cross-section of the eye focused, but no matter what kind you look at, there's the common pivot point of this one. There's the common pivot point of this one, and there's the common pivot point of this one. They're all on that pivot point. And there's even, to really adjust the focus, you can actually drop a little focusing stick into the common pivot point, which I'll show you in a second. You can adjust the magnification by either changing the eyepieces. These happen to be 10x, but there's usually somewhere you'll find in a drawer in the office somewhere some other magnification eyepieces, or by changing the objectives on this stereo microscope. See, it's 1x here and 1.6. When you flip this little lever to the other side, then the objective lens, you see, flips in and out of position like so. The other style of slit lamp has a kind of an odd-looking magnification change because you see it goes 5, 12, 20, 30, then 12 and 8. It seems a little like, why would they do that? Just doesn't make sense, and it's kind of annoying when you're flipping through. Well, the reason is it's actually an elegant solution to the problem because in that circle, if you look at the diagram here, there are little Galilean telescopes. And so a forward Galilean telescope would give you a 30 of magnification, but the reverse Galilean telescope gives you 5. Same with 8 versus 20. But here it's 12 and 12 either way, and that's because see the little dotted line in there? There's no telescope in that one. So it is very elegant, but it's still kind of annoying. Here's the focusing stick I mentioned, and so you can use that to make sure that the slit and the eyepieces are all focused in the same place at the same time by adjusting accordingly. If you find yourself getting headaches when using the slit lamp, it could be that the eyepieces are way out of alignment. So just with any other instrument, if you have a focusing stick, great. If not, you can use the edge of conjunctiva or something and sort of where you can really tell that the slit's in focus the way it's supposed to be, and then you adjust one eye at a time. Pachymetry is next. We use that to measure corneal thickness and anterior chamber depth. And we'll just mention it briefly because it's kind of not really used anymore, but there is an optical pachymeter that used to be used attached to the slit lamp where you get, again, a simultaneous image of the object and the image through a doubling prism. Adjust the doubling prism, use your vernier acuity to find an endpoint, and that gives you the anterior chamber depth when the front of the lens touches the back of the cornea in the image. Now this is generally done with either ultrasound biomicroscopy or even anterior segment OCT. You get a much better measurement of corneal thickness, endothelial thickness, etc. The Applanation tonometer. The Applanation tonometer is a split field plastic prism, we'll explain why in a second, where increasing the force against the eye expands the diameter of a fluorescein-enhanced tear meniscus. And what you want is, once you have expanded that tear meniscus to exactly 3.06 millimeters, then the pressure against the eye in dynes is equal to 1/10 of the intraocular pressure in millimeters of mercury. Now, so what you have to do, imagine trying to do applanation without this split field prism. What you'd have to have in the slit lamp is a little ruler attachment or a reticle, and you'd have to flatten the cornea till you had it just exactly that diameter. Now that one, it looks like it's probably a little too much force, so then you'd sort of back off, and that's not really quite enough. But there, that looks about right, or maybe not. Is it right or isn't it? Hard to say exactly. So it would be an imprecise measurement. So what we have in the applanation tip is a split field prism that separates the images by, guess how much? 3.06 millimeters. This way, when you have too much force, it's obvious because these overlap. So now you back off a little bit. Whoops, that's too far, too little force. Now the circle's small, too small, so they're separated by too much. So then we increase it again, and that's just right, where exactly 3.06 millimeters of separation. Notice that you're using your vernier acuity to find that break in the line and make that precise adjustment. Now, why do we have there's this little red line on the tip, thing that holds the applanation tip. What's that doing there? Well, that has to do with when an eye has astigmatism. Because if astigmatism is present, then the applanated area will be elliptical, so then it's hard to tell when you have the right diameter. So how do you compensate, and what kind of a problem does that lead to? Well, here's an eye with a high astigmatism, flat horizontal meridian. So in fact, mathematically, this is the proper reading because you want to be at basically 58 degrees, I believe, to the major axis of the ellipse to get the exact measurement. So this is actually right, but it looks like it's wrong. So you back off on the knob, and then you end up with an artificially low reading. If you measure, so say you rotate the Applanation tip now 90 degrees and measure this way. It's like, oh, now that looks like it's not enough separation, so you're going to incorrectly dial up on the knob and get an artificially high reading in this meridian. Ah, there we go. Now we're oblique, and so this is the correct one. So if you can be oblique, then you get it just right. So the red line, if you put the red line in the axis of minus cylinder, that places the split field prism at the proper oblique orientation for measuring astigmatism. Now, in my practice, I usually don't bother to do that. I just measure this way, and I remeasure this way, and I take the average of the two. And that is just as close an estimate as measuring obliquely. And I actually managed to cure a child of his glaucoma post-trauma when he had a large astigmatism from the corneal trauma and also had glaucoma. I cured his glaucoma by measuring the pressure in the correct way. And again, why 3.06 millimeters? I mentioned this, they didn't forget to put a 0 on there. This is the force against the eye in dynes. And so it's 1.4 dynes when it's 3.06 millimeters applanated corresponds to 14 millimeters of mercury pressure against the eye. As we say there. Next comes fundus lenses. And have you ever wondered why, like if you can see the cornea so great and the lens so great, why can't you just push the thing that much closer to get a nice view of the retina without having to deal with putting an extra lens in place? Trying to do that here, and it's just not working. The problem is, don't forget about this front of the eye has that 60 diopters of power. And so as you move the slit lamp closer, the light coming in gets converged, and you can never get more than about a third of the way back from the lens to the retina. So fundus lenses have to undo that in one of a couple of ways. One would be to essentially flatten the cornea, and the other is to use indirect ophthalmoscopy. So here we have a minus lens, and another is a minus lens. So the minus lens diverges the light on the way in, so now it can make it all the way back to the retina so you can see it, and that's the Hruby lens. So the Hruby lens is a minus 55 diopter lens. It gives you an upright image of the fundus with minimal magnification distortion. It's actually a very quality image, but it's kind of cumbersome to use, so we tend not to see it used very much anymore thanks to the indirect methods. The Goldmann contact lens, you can think of it as a minus lens. You can also think of it as just replacing the front of the eye with a flat surface and neutralizing all the corneal power, again, to get you all the way back to the fundus, has the advantage of the mirrors that let you look into the periphery. The 90 diopter lens, completely different optically. This is a plus lens, not a minus lens, and it gives an aerial inverted image, just like with indirect ophthalmoscopy. That's why when you put up that 90 diopter lens, say you're focused on the cornea, and then you put up your 90 diopter lens, you have to pull the slit lamp way back because you're pulling it back to look at this aerial image of the retina. The 4-mirror gonioscopic lens also has a central flat area. Don't forget to look at the fundus, so that's one more way to get in. The operating microscope, just very briefly, it has a binoculars, a magnification changer, and an objective lens. You can, when you change your zoom, you'd like it to stay in focus, and ideally you do that before you do your surgery, setting the eyepieces to 0 and the zoom to max. Then you focus the microscope, moving it up and down on like a 4x4. Then you change all the way back out to 0, and now you focus the eyepieces again. With those steps, you can make the microscope parfocal so that it won't go out of focus as you zoom in and out during the procedure. The direct ophthalmoscope we mentioned earlier uses the optics of the patient's eye as a simple magnifier. But notice that if the patient is myopic, then that means there's a plus error lens in there, so it's like a Galilean telescope. So you get extra magnification looking at a myopic eye, whereas the patient's hyperopic, it's like a minus error lens inside the eye. So that's a reverse Galilean telescope, minified. So that's why you may have noticed with the direct ophthalmoscope, it's a little easier to look into the eye of a hyperopic patient than a myopic patient because it's also less magnified. And then one thing is when you're doing direct ophthalmoscopy, only some of the light is making it all the way to the examiner. The indirect ophthalmoscope has this condensing lens that captures the peripheral rays and brings them into the observer's eye. It used to be done with this monocular indirect ophthalmoscope, but then Scapins invented the binocular indirect ophthalmoscope. Oh, this is just the field of view again. So 7 degrees with direct ophthalmoscopy, 25 degrees with indirect because of the condensing lens capturing those peripheral images. When you're doing binocular indirect ophthalmoscopy, the challenge there is to image both pupils and a light source in through the patient's pupil without getting a lot of glare to occur. But that's basically what's accomplished with this. If you've ever, so you're forming basically an image of the examiner's pupils in the patient's pupil, like so the light and the examiner. If you've ever looked at the small pupil type of indirect ophthalmoscope and turned the knob and wondered what happens, what you need to do is you need to move the pupils even closer together now. That's like a 15 millimeter separation. And the light source is up there. If you've got to image those into a smaller pupil, you pull the trigger and voila. Now they see everything's even closer together. So you can get in through the smaller pupil with that setting, but you're going to get less depth perception and more glare. So when possible, you can use it in the large pupil setting, but if you have to, at least you get an image in the small pupil setting. And so because of this, having to do this, it does reduce your pupillary distance from 60 millimeters down to about 15. This, by the way, is a prism that has total internal reflection right there. So that's 60 down to 15 millimeters, which would reduce your perception of stereo by about 4-fold. I learned that the hard way when I was a medical student, all gung-ho, wanted to do everything I could, and there was a grand rounds with a live patient there and a line of people examining with the indirect scope. So I borrowed the lens from the resident and put on the indirect hat and took the lens and wham, hit the patient right in the side of the head with my lens. Oh, sorry about that. My depth perception was reduced. I didn't know that at the time. I only learned that a couple of years ago. So what kind of magnification do we see when we're looking at when we're looking into an eye? The magnification is the power. It turns out, if we do the math, it's the power of the eye divided by the power of the indirect lens that we use. It's transverse magnification. So we know the power of the eye is roughly 60 diopters. And so for a 20 diopter lens, the magnification is going to be power of the eye is 60 over 20 is 3x, power of the eye over the power of the lens. Now remember though, transverse magnification squared gives you the axial magnification. So that means if it looks 3 times bigger across, and it's say a nevus, then it's going to look 9 times deeper. So you're going to get some distortion of depth when looking at the indirect ophthalmoscope. But then, remember what I just said, is the eyepieces reduce your appearance of that depth by 4-fold, so that the axial elevation actually appears to be 9 divided by 4, or 2.25x. So this nevus that you're looking at in the eye is 3 times across, but 2.25 times bigger. So there's a little bit of flattening or depth distortion that occurs. Different lenses, though, give different powers. If you look at the 30 lens, it's a 1-to-2 flattening. If you look at a 15 diopter lens, it's a 1-to-1, no flattening. So you say, does that mean we should actually be using 15 diopter lenses when looking at tumors in the eye? And the answer is no, but you need to be aware that if you switch from one lens to another, you're going to get a different perception, and you shouldn't interpret that as a change in the tumor. Retinal angiography, we already discussed briefly. Fluorescein absorbs in one wavelength, emits in a different wavelength, and you use filters to get the two, to get only the wavelength of interest back out. Lasers. How do we make, what is laser light? Laser light is monochromatic, that is, all photons have the same wavelength. It is coherent, remember that? All the peaks are in sequence. That means you can produce an interference pattern. It is polarized, remember that? Orientation of the electrical field of every wave is in the same orientation. It is directional, that is, it doesn't spread. You can bounce a laser off the moon and get the light back. In total, you can deliver a large amount of energy to a small area with laser light. There are different kinds of lasers. There's continuous wave and pulsed. Continuous wave, the energy per application is varied just by changing a shutter setting. The longer the exposure, the more the energy you deliver. But a pulsed laser, the power comes out as a burst, and so the watts vary over time. And so you keep the time of delivery constant, but measure it in joules, which is a watt delivered for 1 second. So if you see a laser has a power setting in joules, it means it's a pulsed laser, not a continuous wave laser. The three basic ingredients to a laser. We need a pulsed power source to make energy, we need an active medium to emit photons, and we need a chamber with mirrors at opposite sides. So let's look at that, and I'm going to walk over here because it's easier to stand next to the laser while we build one, just to help understand how it works. So here's our chamber, and we're going to put a mirror inside of it, 100% reflecting this side, 98% reflecting on this side, 2% transmitting. Now we're going to fill it up with some source, with a photon emitter, whatever we choose. That's usually what the laser's named after, whatever this substance is. And now we got to get it to release photons, so we pump it with an electromagnetic pump. So this pump, every time the pump hits the emitting substance, more photons are released. So you pump, 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 and each time the pump comes out, more photons are released in an exact sequence, so that's what gives you coherent light, is that steady pumping in the right sequence. Then the light bounces back and forth, on average, because that one's 98% reflecting, 2% transmitting, on average 50 times, and on the 50th time it's gone back and forth so many times you have directional light, so that on the 50th time it bounces out, and out comes coherent, directional, monochromatic light. And that's your laser. Monochromatic because those photon-emitting substance only emits one kind of photon. So what do you do with that kind of power? Well, you can burn things, you can blow them up, and you can sublimate or dissolve them, basically, separate them by sublimation. You burn things with photocoagulation. Energy is absorbed by the tissue, and you get a rise in temperature. You can blow them up with lots of energy, plasma formation and shock wave, or you sublimate by disrupting covalent bonds. Let's look at some examples. Burning things, photocoagulation. We use different colors of light from blue-green to infrared. The blue-green's absorbed by most everything it passes through, RPE, xanthophyll, iris hemoglobin. But then as you go closer and closer to red, red is really absorbed mainly by melanin, and diode is absorbed solely by pigment epithelial melanin, nothing else. So with a diode laser, doesn't matter, you can treat from the outside through sclera or from the inside through pupil. It all goes into the melanin and creates an intense heat in the pigment epithelium only, and that's how you burn the retina. The YAG laser is infrared light, where you have these high power pulses that are focused into a very small area, causing plasma formation, optical breakdown, basically a little explosion. And so absorption is not necessary, and that's why we can use the YAG laser to cut semi-transparent membranes like the posterior capsule of the lens. And then we have the excimer laser, which is at the other end of the spectrum in ultraviolet, high power ultraviolet radiation. That's absorbed by all eye layers, even by the water. even by tears. So the cornea gets most of the energy. You actually want to remove the tears to treat with the excimer laser. And the damage, it's not burned, it's not blown up, it's more like an insurgency. It goes in and it disrupts the covalent bonds that hold the tissue together, that hold the molecules together. There's no heat, there's no fuss, things just sublimate. And so this was one of the early excimer lasers when they were thinking of using it more like a knife, and you get this nice, beautiful mushroom cloud of sublimated material disappearing off into space. It looks beautiful, but of course if you're trying to treat a big patch with the excimer laser, that's going to cause an irregular ablation and diffraction and distortion and glare and all those things. So you need a fan to blow all that stuff out of the way before the next pulse comes in. Otherwise, you'll get bad pulses. So that's ophthalmic instruments. And as the final step, I just want to talk about some key symptoms. And we'll run over by a little bit. I don't think by too much. I want to talk about some key symptoms that will bring patients to you that may have something to do with the optics of what they're looking at. And just, I mean, if you think about it, if you were, say, an oral examiner or something, you've got to have clinical scenarios that are relevant that still allow the candidate to show their understanding of optics in a clinically relevant way. So we're going to talk about double vision, bad glasses, poor vision, and headaches and asthenopia. It's not a super long section. So patient comes into your office with double vision. Well, the very first thing is to find out if it's monocular diplopia or binocular diplopia. And the diagnosis is simple, but not as simple as you think. Have the patient cover one eye, and if the double vision is still there, then it must be monocular diplopia. But you have to have them cover the right eye, because what if the left eye has monocular diplopia, the right eye doesn't? If they cover their left eye, their monocular diplopia will go away. That just happened to me just like Saturday. I saw a patient post-op because I'd done her adjustable suture strabismus surgery, and she said, "Oh, the double's worse than ever. It's everywhere I look. It's horrible." And so I brought her in. I thought I'd have to readjust. But it turns out she had a little epithelial defect that crossed right across her pupil, and she had monocular diplopia. And when she covered her left eye that had surgery, yeah, everything was single. When you covered the right eye, though, she had clear double vision, went away with a pinhole. So the causes are then surface problem. Just refractive error alone can cause monocular diplopia. Don't know if you've ever experienced that. I've certainly seen it. Midpoint in a refraction, sometimes a patient will tell you that. Irregular astigmatism. A lenticular irregularity, such as cataract, only rarely can a retinal problem cause this. That's the only one that wouldn't go away with a pinhole. The most common scenario, I would say, is a patient comes into your office, monocular double vision. You sort of narrow it down either to dry eye or to an early incipient cataract that's just enough to cause this double vision. And once you explain to the patient that they don't have a brain tumor, show them that it goes away with the pinhole, they're usually satisfied and then you can address it as best you can. Okay, patient comes into your office. It's definitely this time, it's binocular diplopia. You cover one eye, it gets better. You cover the other eye, it gets better. With both eyes open, they see double. So what do? Well, you do cover testing, prism and cover testing to look for strabismus, of course. But sometimes the strabismus can be subtle and not that visible. You want to look for prism in the glasses. Now, sometimes the prism can be there by accident. Just as I said, a patient drops their glasses and the lenses go in upside down or they get reversed or something like that. Even more subtle is, and again I've seen this, a patient might have had a superior oblique palsy and an optometrist 10 years ago gave him prism glasses, and each refraction after that someone's kept the prism glasses going, but now finally someone gives them a prescription and doesn't realize that there's prism in there. Now all of a sudden with the new glasses they have double vision. I guess I'm jumping ahead of myself, but you can do a red glass or other sensory test, and really if it's true binocular diplopia, for the most part, except for what we'll just talk about, it's more of a strabismus issue that you kind of go into that mode. New glasses are no good. I described the scenario. Give the patient their new glasses. It's especially challenging if the new glasses were the exact same prescription, but you do want to compare. If possible, get the old glasses. Compare the axis and the power. Compare the base curves. Look for prism, unintentionally ground in. I mean, intentional prism that's been ground in, or unintentional because the optical centers are off axis. Consider trauma to the glasses, as I've also mentioned. Look for the astigmatic grinding, the front and the back surface. It gives you a chance to sort of show off your knowledge of lens clocks. Look for different coatings or tints. All of these things can potentially have something to do with the patient who's unhappy with glasses. We were just discussing at the break a patient who might have had a reduced distance, plus they had a myopic shift at distance, and so the bifocals used to be good, but now because you've taken away plus from the glasses, that means their effective bifocal power is also reduced. That could be another cause of new glasses, no good. Yeah, and here we are, check bifocals. So the power might be off for the reason that I just said, or for other reasons. The segment height could be off, especially in the progressive ads. The design may have changed from progressive to flat top or vice versa. A patient just recently, again, bitterly complaining about her new glasses, and it was because if she moved her head side to side, professor type, right, engineer type, if she moved her head side to side, then she'd see this wavering in the image. So that's why her new glasses were no good, and she went to a segmented bifocal. Check the refraction. Look for cycloplegic refraction because maybe they've been over-minused. Look for a big change in the cylinder, and look for a rapid change such as cataract, and then that throws us into that whole differential diagnosis. All these things are sort of things that you kind of know. You would know when you're sitting in front of a patient and have them in front of you, but you might not know when you're sitting in a hotel room across the table from someone who has a book that has the answers in it. Poor vision after refraction. Remember I said a long time ago when I started, was a month ago or so, that you do your best refraction and the vision's still bad. Well, why would that be? Well, maybe your refraction wasn't that good after all, so put the pinhole occluder up now after you're done with the refraction. See if it gets better. Say it does get better. Well, maybe your axis is off, or they still have poor vision, so get out the high power Jackson cross cylinder so you can really truly refine the astigmatic axis in a way that the patient can make their choices. Look for dumb stuff. Maybe the eye chart contrast is off, the bad lighting on the eye chart. Consider subtle disease. You're still allowed to have disease, even in the optics section and in real life. Latent nystagmus would be one notable and notorious thing that can cause reduced vision with one eye covered. Recheck vision with both eyes open to see if it gets better. And dry eye as well. Often patients, even in the course of a refraction, I'll have to tell them to just stop and blink a few times and the vision will magically improve. A lot of magic in this. Headache and asthenopia, another big topic. Patient comes into your office complaining of headache, tired eyes when the glasses. So they're not saying they're no good, but they're specifically complaining of headaches. Cover testing, look for those phoreas and tropias. Again, maybe induced by glasses that had optical centers that were off. Look for prism in the glasses. Again, either new prism that shouldn't be in there or prism that used to be in there that you didn't notice and forgot to check. Check the refraction, of course. Latent hyperopia would be a primary cause of asthenopia and headache. Not enough plus power, causing the patient to have to work hard to accommodate, or overcorrected, over-minused, again causing the patient to over-accommodate. Or a patient may just have early presbyopia and be having to accommodate in that way. So in the last couple of minutes, just this what we covered in this part 4 was the review of the formulas, prescribing glasses, instruments, and a quick rundown of optics in the office and how that works. And I just want to say that I know that a lot of you are studying for an exam right now, and you're mostly worried about that. But I'd like you to think of it as an opportunity, if you can sort of get to that level, that some of this stuff actually makes a difference. Some of this stuff really does help you, make you a better doctor. Furthermore, it can make things more interesting when you're taking care of patients. It can help you take care of that, anyone can get the 90% of patients, but it can help you take care of that last 10% of patients who have tricky problems, who need a little more thought, thinking outside of the box, and working on it a little bit more. And as a result, it makes your life and your practice, enhances it in a different way than it would otherwise. So that's really my job today. And optics, I know for all you say about it, just last Sunday in the New York Times Magazine, will take this out of context. This is taken out of context, but the quote was appropriate. The beauty of optics is in the eye of the beholder. So thank you all for your attention today, and I hope this does help make you better and more satisfied doctors. Thank you.